this is Professor Cummings, and this is a follow-up video to my video for epicyclical gears or planetary gears. And I went through in that last video kind of the function of them, the concept of how they worked. And in this video, I want to go through calculating how you would calculate the inputs and outputs of these gears. And I want to use a method called the tabular method. Well, the tabular method is a pretty easy method of doing this. It's actually very intuitive once you see it run through a few times. And in this video, I'm going to just go through the concept of how to put that table together. And then in another video, the next follow-up video, I'll actually give you an example. I don't want this video to be too long as I go through this concept, and you really want to just lay it out and explain why you're doing what you're doing. Now, in order to understand this, you got to understand some of the basic ideas behind gearing in general. Then these are some of the universal ways gears work. So what I'm going to go through in this video is first go through the idea of gear ratios. So I did this in another video, so I've got two videos on gearing, but my video on basic gearing, I went through gear ratios and how to come up with them. So I want to review that a little bit because that's going to be key. I want to go through the sign convention. In planetary gears, in order to understand which direction the input and output are going, and there's all sorts of little things you can do to end up changing that. You can it's important to know what the sign of the gear is going. So which direction the gear is turning is going to be important to know, how these gears are actually interacting. I want to talk about the implication of the arm or the carrier. Now I use those terms interchangeably. In some application you'll see it called the arm, in some application you'll see it called the carrier, and I'm just gonna I think I say the arm probably the most in this video, so we'll just say the arm of the system. And as you know, planetary gears are made up of a sun gear. Let's see here, the sun gear, the planet gears that are rotating about the sun, and an annulus. And the planetary gears are actually connected through something called the carrier or the arm. And then once we've looked at all the different players in the planetary gear and how they work in their calculations, I'll show you the total motion of the gear train. So the input to the output and how that's done, and why the table is important to keep your thoughts and everything organized. So let's go through this, and we'll start with a little bit of review. So the velocity ratios. So the velocity ratios can be calculated based on just any two meshing gears. Now in this little GIF here, you have a gear with 60 teeth, that's the driver, a gear with 30 teeth that's being driven, and as you can see in the GIF, the one gear, they're actually going at pretty different speeds, 30 teeth to 60 teeth. You can see the smaller gear is actually rotating much faster. That angular velocity is much higher with the smaller gear with the lesser teeth. So this is how the gear ratio actually works out. So you got these gears. They're clearly going at two different rotational speeds, but they have a common speed, and that's known as the tangential speed, where they actually mate. So their speed between both the gears are actually one common speed, whatever that might be between these two. And it is that common speed, or known as a tangential speed, is just the radius of gear A times the angular velocity of gear A, which is also equal to the radius of gear B times the angular velocity of gear B. These two are equal, and they come to the same common tangential velocity. All right, the bigger the radius of A, the smaller the angular velocity, and the smaller the radius and the higher angular velocity. So there is a proportional relationship between both the diameters of the gear, or radius of the gear, and the angular velocity of the gear. There's also a proportional relationship between the number of teeth that are engaging in gears. That's also part of the velocity ratio. So you can see there's a relationship in the angular velocities, the radiuses or diameters, and the number of teeth. And in this particular instance, the velocity ratio of 60 teeth to 30 teeth would be 2. So that's the idea of the velocity ratios. Now keep in mind, this is a concept that goes between gears and how they mesh, and it's going to play up, very big in planetary gears. Also, another important point, notice that in this particular setup, that the direction of gear A, when you're dealing with external gears, is the opposite of gear B. So that when you merge gears together, you're going to get an opposite rotation out of the reacting gear. Two important points that I want to bring up. Now, when you've got planetary gears, you're dealing with, again, a sun, a planet that rotates about the sun, and an arm gear, or an arm, or a carrier. Now, in one condition, the first condition of breaking down, planetary gears and trying to understand how they behave, we will look at the arm, or look at a condition where we take the arm and actually keep the arm fixed. So you got planetary gears, and you're not allowing the arm to move. In this condition, it looks no different than any other standard gear train. You've got one gear rotating and forcing the other to move. And you've also got, the condition of the velocity ratio at play. The only thing this arm is doing is it's just something that's holding the gears together. So the arm is fixed. There's no motion on the arm. And again, you can treat this as just a standard gear train, but there's something important to keep in mind when you think of that standard gear train, and this is why velocity ratios are so important. One revolution, if you just take one revolution of gear A, based on that velocity ratio, we're going to get a proportionate number of revolutions in gear B. All right, so that means if I take gear A and rotate it one time, that I'm going to get 2 in this 2-to-1 velocity ratio, 2 rotations out of gear B. Another way of looking at this is, let's say we don't know how many rotations or how fast it's going, because velocity takes into the same place. We know that if we rotate this by x, the velocity of x on gear A, that the velocity at gear B is going to be x times whatever that velocity ratio, and in this case it's going to be NA over NB, and it's also going to be in the opposite direction. And in this case, we'll say that gear A is turning in a positive, gear B is going to be whatever opposite that is. So if gear A is going in a negative direction, and we'll go into sign convention quickly or soon here, we'll see that gear B is whatever gear A is with the minus sign to it, to represent it's going in the opposite direction. So that's the condition. We'll say conditions 1 and 2. Condition 1 being if you rotated, in direction 1, made 1 revolution. Condition 2 is if you give it a certain speed on gear A, you're going to, in both cases, see it, the difference or the reaction in gear B is going to be proportional based on the velocity ratio. Again, keep those in mind. So in gear A, you got the arm is fixed. The rotation of the 2 gears are in opposite direction, and you've got, in this case, gear A going clockwise, and we're just going to arbitrarily say that clockwise is negative. That's the general convention or standard convention for epicyclical gears or planetary gears, but we're just going to say, just go with this one and say that it's, the gear A is rotating in the negative direction because it's going clockwise. That means gear B is going in the positive direction because it's going counterclockwise, or as some people say, anti-clockwise. So this is our sign convention for gearing, and that's going to be very important to keep in mind, because especially with epicyclical gearing, there are several conditions where you can change the gear's direction, and that's going to be very important as to what you're getting as its output. Again, when gear A makes X rotations, in the clockwise direction, you can expect gear B to make a proportional based on X in this velocity ratio in the positive direction, counterclockwise. Now, let's look at a condition, or imagine a condition where an entire rotation is based around what the arm or the carrier is doing. Now, what I mean by that is, assume this entire system is locked up and we're just turning the arm in a particular rotation. Let's just say in a positive direction. We'll say positive, we're doing a positive number of RPMs is Y. So it's rotating in the positive direction, counterclockwise Y. So the rotation of the arm, what that does is the arm actually compounds the rotation of the gears. So rotation of the arm going in a positive Y direction. So if we were to turn this again counterclockwise at a particular speed, and again I'm just using Y as just the variable representing the RPM, it adds to the real rotation speed of the planet and the sun gear. basically there is a relative speed between what the arm or the carrier is doing and both the sun gear and the planet gear. And remember, the sun and the planet gear are rotating in opposite directions of one another. Again, keeping this same convention, let's just say that this arm is rotating in a positive direction. All items are rotated relative to that arm. So keeping that in mind, again, keeping the rotation is relative to the arm. And the last condition is the real speed or the total motion of the entire system. So in this case, again, we've got the arm rotating in the positive direction. And as you can see, the sun is rotating in the positive direction. And the planet gear is actually rotating, based on the sun. And just ignore the annulus gear for now. So the rotation of the arm, like I said, compounds the rotation of the gears. And a rotation of an arm in a plus y RPM adds to the real rotation speed of the planet and gear. So what does this mean mathematically? How are we going to add this in? So rotation of gear A, like we had said, if we just are spinning that in the counterclockwise direction at x RPM, what does that do to gear B? It rotates it in its opposite direction of x, a negative x, by the velocity ratio. So whatever proportion of that speed is going to be attributed through the velocity ratio. And if we're rotating the arm, which is going to compound the speeds or make a relative difference in the speeds, there's going to be a total speed of the arm which is going in the y, the positive direction counterclockwise. The green is going in the counterclockwise, so a positive y RPMs is going to compound on the two gears. So the total speed at gear A will be the speed of the arm plus whatever is going on with gear A, which is x RPM. So you're adding the RPMs together. Whereas with gear B, the planet gear, you're actually subtracting from what the arm is doing. So again, it's a relative speed to the arm. Everything is relative to the arm. So now let's look at this using the tabular method. Let's go ahead and create the table for this particular system. So again, we still got our planetary gears, basically the same thing, just a slightly smaller version of it. And we're calling gear A the sun, gear B is the planet, and gear A is obviously going in the positive direction, the counterclockwise direction, and gear B is going mating up in its opposite, and the arm or the carrier is going in the counterclockwise direction as well. So again, we got the counterclockwise rotation is positive, the clockwise rotation is negative, or anti-clock rotation is negative, or excuse me, anti-clock is positive, clockwise rotation is negative. So let's create the table. So again, we got the step, we got the conditions, we know what the arm is doing, we know what gear A is laid out, and we got gear B laid out. So let's look at our conditions. So in first one that we went over was the arm was fixed, gear A makes a +1 revolution and rotating in counterclockwise direction. So the arm is doing nothing, gear A is rotating one time, and we know that gear B is going to move based around the gear ratio in the opposite direction. All right, this next one, the arm is fixed and gear B makes a positive X rotation. That should be gear A, that's actually a typo. So gear A is going at +X, and the RPMs of gear B is going to be a negative X opposite direction, going based on the gear ratio in A over in B. Now, when we look at all the elements rotating based around the arm going to the counterclockwise direction, we're just going to add or compound what the arm does. So everything's getting a positive counterclockwise rotation based on how fast that arm is rotating, which gives us the total motion. The arm's total motion is still the same. It's just going in the positive Y direction, counterclockwise direction. Gear B is compounding it by adding to the arm, and gear A is adding to the arm, so it's X plus Y, and gear B is just subtracting from the arm. So it's the ratio of x, the rotation, imparted rotation from A, based on the velocity ratio of B. So this is the layout of the tabular method. Okay, this is the layout of the tabular method, and I'll go through and give you an actual example with actual numbers and a full-blown scenario in my next video. So this is Professor Cummings, and I want to thank you for watching, and go ahead and thumbs up, like, subscribe, or visit the engineer's reference, where this video will also pop up, as well as a few others on mechanical engineering topics. But thanks for watching.